Section: Introduction. In this section, we explore how large language models, LLMs, which have shown impressive abilities in solving complex reasoning tasks, can be made to reason without the usual methods of prompting. Typically, to get these models to reason, researchers either provide them with a few examples to follow, few-shot prompting, or give specific instructions to show their work, zero-shot prompting. Another common approach is to train the models on a lot of data that requires reasoning through a problem step by step. However, we ask a different question. Can these models reason on their own without any prompting, and if so, how well? Surprisingly, we discover that it's possible to get pre-trained LLMs to show reasoning simply by changing how they generate answers. Instead of the usual way where the model might jump to a wrong answer, we look at alternative options the model considers but usually ignores. By doing this, we find paths that the model could take that actually solve the problem correctly, showing a kind of reasoning we call chain of thought, COT, reasoning, without needing to prompt the model in any special way. This approach is unsupervised, meaning it doesn't require additional training. To put this into context, when we usually ask these models a question, they tend to go straight for an answer, which doesn't always work well for reasoning tasks. But when we allow the model to consider different options before deciding on an answer, we see it naturally starts to reason through the problem. Interestingly, when the model uses this COT reasoning, it seems more confident in its final answer. For example, in one of our tests, the model was more certain about getting the right answer when it followed a COT path compared to when it didn't. Taking advantage of this, we developed a method to pick the most reliable paths the model considers, which we call COT decoding. This method helps us use the model's inherent ability to reason, improving its performance on reasoning tasks without needing to train it further or give it specific prompts. Our experiments show that this COT decoding method reveals natural COT reasoning in the model and significantly improves its ability to reason across different types of tasks. We also notice that the model is better at reasoning through tasks it has seen during its initial training compared to completely new or synthetic tasks, where traditional prompting methods might still be necessary. In summary, our work shows that pre-trained language models already have the capability to reason through problems. By simply changing how we decode their answers, we can bring out this reasoning ability, leading to better performance on reasoning tasks without the need for complex prompting strategies. This finding opens up new possibilities for using these models and understanding how they think. Section Summary. In this section, we explore the reasoning abilities of large language models, LLMs, without explicit prompting. By altering the decoding process, we discovered that pre-trained LLMs can naturally exhibit chain of thought, COT, reasoning paths during decoding, leading to more accurate answers and increased model confidence. Our findings suggest that a simple change in decoding strategy, known as COT decoding, can significantly enhance ILM's reasoning capabilities across various benchmarks, without the need for explicit prompting. Section: COT decoding for extracting COT paths. In this section, we discuss the process of COT decoding for extracting chain of thought, COT, paths. We've noticed that even though COT paths naturally occur, pulling them out from the top choices decoded by the model is quite tricky. Our observations show that COT paths don't always get the highest rankings in the model's probability assessments compared to non-COT paths. Moreover, they often don't align with the most common answer, which makes methods like self-consistency not very useful. For example, in a specific math question, the most common answer, 60, didn't help in pinpointing the correct reasoning path. Interestingly, when we looked closer at the model's confidence levels, indicated by its logits, we found that the presence of a COT path usually means the model is more confident about the final answer. This confidence is measured by the difference in probabilities between the top two choices at each step of decoding, averaged over all steps that contribute to the final answer. For instance, if the answer is 60, we calculate the average difference in probabilities for 6 and 0. This approach, which we call COT decoding, helps us identify COT paths among the various paths the language models generate. We've seen that paths with a COT component have a significantly higher confidence difference, which is a good indicator of the model's confidence. Additionally, we've considered the length of the decoding path as a heuristic, thinking that longer paths might be more likely to contain COTS. This idea works to some extent for math reasoning questions, but it's not as effective for other types of reasoning tasks where the lengths of the decoding paths don't vary much. To identify the correct answer span in a model's response, we've tried a couple of methods. One simple way is to pick the last numerical value in math reasoning tasks or the final option in set-based reasoning tasks. This method is generally effective but can be thrown off by distracting numbers or options. A more refined approach extends the model's output with the prompt, "So the answer is," and then aligns these continuations with spans in the model's decoding path. This technique is quite flexible and works for both mathematical and natural language reasoning tasks. It's important to calculate the confidence difference over the answer spans from the original decoding path to avoid reinforcing incorrect probabilities. In cases where the answers are more open-ended, using the probability differences of the top two choices as an indicator might not be as precise. If the answer options are clear-cut, like yes or no, we could adjust the calculation of the confidence difference by focusing on the aggregated probabilities for each option. While this method has been useful for yes-no questions, its effectiveness for more open-ended questions remains to be explored further. Lastly, we've looked into whether it's beneficial to consider alternative tokens at different stages of decoding, not just the first one. Our analysis shows that branching out early on can significantly increase the diversity of potential paths. However, branching out at later stages tends to be less effective, as the choices made in earlier steps heavily influence the path's direction. The best point for branching may depend on the specific task at hand. For example, in tasks like the year parity task, branching at a midpoint can successfully lead to correct COT paths. Section Summary. In this section, we explore COT decoding for extracting COT paths, which are challenging to identify among top K-decoded paths due to inconsistent model probability rankings. By introducing a method called COT decoding, we aim to extract COT paths by analyzing the model's confidence in decoding final answers, indicated by significant probability differences between top and secondary tokens. Additionally, we discuss strategies for identifying answer spans in model responses, emphasizing the importance of calculating confidence levels over original decoding paths rather than those extended with prompts like, "So the answer is," to avoid reinforcing incorrect probabilities. Section: Aggregation of the decoding paths. In this section, we discuss how we combine the top K decoding paths to improve the model's performance. Instead of just picking the single best path based on the highest score, we look at multiple paths and combine their results. This method is somewhat similar to asking the model to check its work, but we do it without needing a specific type of prompting called chain of thought, COT. We noticed that just picking the most popular answer doesn't always work out well. So, we came up with a better strategy where we give more importance to answers that show up in paths with higher scores. We add up the scores for each answer across all paths, and the answer with the highest total score is chosen. This approach helps make our results more reliable. Next, we explored whether using a technique called sampling could help us find COT reasoning paths in a standard question and answer format. Sampling is a way to generate answers where the model can take more varied paths by introducing randomness. We tried this by adjusting the randomness level, temperature, and generating multiple answers for each question. However, we found that this method wasn't very effective for our purpose. Most of the time, the model skipped the reasoning process and went straight to giving an answer, which often wasn't as accurate. For example, when we asked a question, the sampled answers varied widely and usually missed the reasoning steps we were looking for. We also conducted experiments to test our COT decoding method across different reasoning tasks. We set up our experiments using a standard question and answer format and chose a default setting for our decoding process. We tested our method with various models, including both pre-trained models and those that had been further trained with instruction-tuned models. For identifying the correct answers, we used different strategies depending on the model. Our results showed that our COT decoding method significantly improved the ability of models to reason through problems, especially on math reasoning tasks. This improvement was consistent across different sizes of models. Interestingly, we found that our method could even enhance the performance of instruction-tuned models, which were already trained with lots of reasoning examples. This suggests that our decoding approach can help models explore different ways to solve a problem, leading to better answers. Section Summary. In this section, we aggregate the decoding paths by considering the top K paths without COT prompting to reduce sensitivity to small differences in model logits. We propose a weighted aggregation method that maximizes the sum of delta values across paths, enhancing result stability. Sampling under the standard QA format shows that COT decoding outperforms sampling in revealing COT reasoning paths, improving reasoning benchmarks without specialized prompting. Section: Scaling results and choice of. In this section, we discuss how the number of top alternative tokens considered, denoted by K, affects the accuracy of our models. We've discovered that choosing a higher K generally leads to better performance. This suggests that the correct chains of thought, COT, paths are often present but might not be ranked highly during the initial decoding process. However, for models that have been fine-tuned with instructions, the choice of K doesn't seem to matter as much. This indicates that instruction tuning is effective at bringing the most relevant COT paths to the forefront. We then delve into the year parity task, a challenge where models must determine if a celebrity was born in an even or odd year. Despite the advancements in large language models like GPT-4, they struggle with this task, often only achieving accuracy around 50% when asked directly. However, these models can almost perfectly retrieve a birth year or judge its parity when given the correct year, pointing to a difficulty in manipulating knowledge rather than retrieving it. We show that by using COT decoding, we can significantly improve the model's ability to correctly reason through this task. To test this, we compiled a list of 100 celebrities and verified their birth years. We then assessed the model's performance by comparing its responses to the actual, even, or odd, status of the year. Using a model directly prompted with the question yielded only chance-level accuracy. But, with COT decoding, the model's accuracy soared above 90%. Most errors were due to the model retrieving the wrong birth year, yet the COT paths generated were consistent with the model's reasoning process. We also noted that smaller models struggled with this task, showing little variation in performance at or below a certain model size. Moving on to symbolic reasoning tasks, we explored several challenges including the coin flip task with varying rounds, and tasks from Big Bench Hard like Web of Lies and multi-step arithmetic. These tasks, designed to test the model's problem-solving capabilities, showed that the effectiveness of COT decoding diminishes as task complexity increases. Moreover, models struggled with highly synthetic tasks, those not well represented in their training data, highlighting the influence of training distribution on model performance. In tasks requiring precise state tracking, like coin flip and Web of Lies, models could generate COT paths that simulate the process but often lost track of states as complexity increased. This underscores the model's inherent difficulty with accurate state tracking. However, using carefully crafted COT examples during training helped teach the models to better manage these tasks. For instance, in multi-step arithmetic, models tended to calculate from left to right, and in object counting, they learned to exclude irrelevant objects before counting, thanks to the targeted COT prompts used during training. Section Summary. In this section, we explore how the choice of the number of top alternative tokens considered impacts model accuracy, finding that higher values of this parameter generally lead to better performance. We focus on natural language reasoning tasks, such as the year parity task, where COT decoding helps models achieve over 90% accuracy by eliciting correct reasoning paths. Additionally, in symbolic reasoning tasks, we observe that COT prompting techniques play a crucial role in helping models solve tasks accurately, especially in scenarios where accurate state tracking is essential. showcasing the model's vulnerability in complex tasks like coin flip and web of lies. Section: Compared to COT prompting. In this section, we delve into a comparison between COT decoding and the existing methods of COT prompting, such as few-shot and zero-shot COT prompting. We start by observing that using an aggregated path approach significantly boosts accuracy compared to just selecting the path with the highest score. This method proves to be more stable as it lessens the impact of minor differences in the model's score predictions. Interestingly, we find that the performance of the aggregated path approach is quite similar to that of few-shot COT prompting. This similarity suggests that the model already has an inherent ability to solve tasks effectively, and few-shot COT prompting might just be bringing the model's natural COT paths to the forefront. We also present examples that highlight the differences in the COTs generated by each method. Notably, COT decoding tends to produce more varied and free-form COT generations compared to the other methods. This difference can be attributed to two main factors. Firstly, we encourage diversity right from the initial step of decoding, and secondly, there are no explicit constraints as seen in prompting methods. Another interesting observation is that COT decoding seems to better uncover the model's natural strategy for solving problems, free from the potential biases introduced by external prompts. For instance, in one of the examples, the few-shot COT path closely follows a standard analytical approach influenced by the prompts, whereas COT decoding reveals alternative, albeit sometimes incorrect, valid paths. Moving on to experiments across different model families, we specifically look at the open-sourced Mistral 7B model. We evaluate both the pre-trained version and the instruction-tuned variant. Our findings show that even when the model attempts to directly answer a question, considering alternative tokens at the first step of decoding can lead to the emergence of COT reasoning. The results across different models consistently show improvements, highlighting the effectiveness of COT decoding over simple greedy decoding, across various tasks including math and natural language reasoning. In the broader context of enhancing reasoning in large language models, many efforts have focused on developing better prompting techniques to elicit COT reasoning. However, these techniques often require task-specific prompt designs and intensive manual effort, limiting their generalizability and resulting in variable performance. Our work, on the other hand, explores a different angle by focusing on the decoding stage. We demonstrate that models can inherently generate COT reasoning paths across a wide range of tasks without the need for explicit prompting. This approach not only sidesteps the need for task-specific prompting but also avoids altering the model's vocabulary distribution in unpredictable ways. Furthermore, while recent works have proposed methods to improve COT generation through various means such as step verification and feedback, these still rely on COT prompting. Our approach is distinct in that it completely removes the need for COT prompting and focuses purely on exploring the decoding space at the token level, using confidence scores to guide the decoding of answers. Lastly, when it comes to eliciting COTs in language models through supervision, methods like instruction tuning or distillation have been explored. However, these methods often require extensive fine-tuning and a large collection of COT-annotated examples, which may not always be available. Our approach stands out as it is unsupervised and leverages the model's intrinsic ability to generate COT paths, eliminating the need for fine-tuning or additional models. Section Summary. In this section, we compare COT decoding with existing COT prompting methods, such as few-shot and zero-shot COT prompting. The aggregated path approach improves accuracy by stabilizing results and showing intrinsic abilities in solving tasks effectively. COT decoding reveals the model's intrinsic strategy without external prompts, leading to more diverse and free-form COT generation compared to alternative prompting methods. Section: Decoding algorithms for language models. In this section, we delve into the various decoding algorithms that have been developed for language models, focusing on their roles in enhancing aspects such as fluency, coherence, reducing repetitiveness, and diversifying responses. We discuss popular decoding strategies like greedy decoding, temperature sampling, top case sampling, and nucleus sampling. Additionally, we touch upon more sophisticated algorithms like minimum Bayes risk decoding and typical decoding, which refine the decoding process further. Another method we mention is diverse beam search, which seeks to explore different paths in a model's generation process, prioritizing diversity over accuracy. Despite the wealth of research on decoding algorithms aimed at improving general aspects of language generation, we note a significant gap in studies specifically targeting the enhancement of reasoning tasks. Some advancements have been made, such as improving upon chain of thought, COT, prompting by sampling and aggregating multiple generated responses to bolster reasoning capabilities. Contrastive decoding emerges as another technique to enhance the quality of model generations by penalizing the logits from smaller models, with recent studies showing its effectiveness in boosting reasoning performance. Proposals for context-aware decoding aim to increase the faithfulness of language models by incorporating more context into the decoding process. These methods often rely on additional resources, like employing extra models for generating contrasting logits or adding more context, whereas our approach is distinct in that it operates effectively using a single model without the need for extra information. Moving on to decoding algorithms focused on efficiency, we acknowledge a significant amount of research aimed at making decoding faster and more resource efficient, such as speculative decoding. This research direction is considered orthogonal to our primary goal of enhancing a model's reasoning capabilities. However, we recognize the potential of these efficiency-oriented techniques to possibly improve the efficiency of COT decoding in future applications.